Okay, in this video, our focus is mostly going to be on concavity of graphs and determining the concavity of graphs. So before we can do that, let's define that word, concavity. So concavity looks at the second derivative. Okay, and concavity tells us whether or not the first derivative is increasing or decreasing. In other words, is the derivative getting more and more, bigger and bigger positive, or is the derivative getting less and less positive or negative, whatever. So first of all, concavity. The graph of a differentiable function y is equal to f of x is concave up on an interval I, so it's concave up on an interval I if the first derivative is increasing. So if the first derivative, if your slopes are getting bigger and bigger and bigger and bigger and bigger, then it's concave up. If your slopes are getting smaller and smaller and smaller and smaller and smaller, then it's concave, what we call down. Okay, so here's a visual representation of what we're saying. So here we have the graph of y is equal to x to the third. You notice here is your point of inflection, or that's where we should say where your graph changes concavity. So on the left side, it's concave down because you notice your slopes. Like, look at all these tangent lines. Look at this first tangent line here. And then compare that to the last tangent line that we drew here. This first tangent line is bigger, the slope of this first tangent line is bigger than that last one. So that means your slopes from x equals negative infinity to 0, your slopes are getting smaller and smaller and smaller. Hence the definition concave down. Then from 0 to positive infinity, so if we look at our first derivative line here, our tangent line, the slope of that tangent line is, now you know it's not huge, but look at the slope of this tangent line. So these slopes are getting bigger and bigger and bigger, hence the concavity is positive, so it's concave up on one side and not the other. All right, so that's graphically kind of what it looks like, and you notice here's another one. This graph, it is always concave up, because you notice you have real negative, like if I drew this one, this is a really large negative, and then here's your horizontal tangent. So it's still getting bigger even though it's 0. And then you have a really large positive slope on this side, and they keep getting bigger and bigger and bigger. Their slopes do. Okay, so this graph is always concave up. Now, in here, the graph of a twice differentiable function is going to be concave up. Whoops. There we go, concave up. If we're going to look at this in terms of your second derivative, if your second derivative is greater than 0 and it's concave down, if your second derivative is negative or less than 0. So let's take a look at this little graph here. All right, on this first one we have a smiley face. Okay, you notice this right here. This is your function. So that is f of x. Your eyes, whoops. I'll do this, the eyes in blue. Your eyes represent the first derivative. Now, this tells you that your first derivative is negative. So here's your critical point. Your first derivative is negative because your slopes are negative. And this I tells you that your first derivative is positive on your graph because it's increasing. Now the nose is your second derivative. Now, when you have negative derivative to a positive derivative on that interval, you're going negative, getting more and more positive. That means your slopes are increasing on that interval. That's why this nose represents a positive concavity. Now, as over here, again, the mouth is our function. So it'd be like negative x squared or something like that. Your eyes are the first derivative. So on this side, positive slopes. On this side, negative slopes. So if it goes from positive slopes, so it goes from increasing to decreasing, then that is an indicator that your then second derivatives are going to be negative. So it's going to be concave down on that interval. So this is a neat little visual representation of what concavity looks like on graphs. So here's another thing. It's going to be concave up if your graph looks something like that. So concave up. So this would be an example of what it would look like to be concave up, and then concave D-O-W-N. Concave down graph is going to look something like this. Generally, not all the time. It's got to look at something like this. So from decreasing to increasing is up, from increasing to decreasing is down. So that's what concavity is, and you have to understand where they change direction or where it goes from one concavity to another, and that's what's called a point of concavity or a point of inflection. And that is where the concavity changes from either positive to negative or negative to positive. So what that means, if you look at this last sentence here, it says if y, let's see if I can highlight this. So this is kind of deep, so pay attention. If y is a twice differentiable function, the second derivative is 0. So if it's twice differentiable, the second derivative is equal to 0 at some point, at a point of inflection, and the first derivative has a local maximum or minimum. So the first derivative has a local maximum or local minimum. Okay? All right. So if we look at this example here, the first function, right here, whoops, this function is this line. So that is your original function. Your other one, y sub 2, is this line down here. That is the graph of the second derivative. Okay, that is a graph of the second derivative. So you notice where the second derivative is equal to 0, here, here, and here, we have what are called points of inflection. Now, obviously, you can't see beyond this point or beyond that point. So let's focus in on the point where we can see the surrounding values. So let's focus in on this point here. Your slopes, if you were to look at your slopes, it goes from positive to negative. So those are decreasing, so that's concave down on this interval. So it's concave down. Then you notice it goes from decreasing to increasing, so then on this interval it's concave up, and it switches right at that point. So that's what we call a point of inflection, where the concavity goes from down to up, and most times it's going to be halfway between. So if you ever have a problem finding, where do your max and mins occur, well, and you don't know what the first derivative is, you just have the second derivative, well, chances are, if you know what your inflection points are, they're going to occur halfway in between. Okay? All right. Down here, just a few things. The second derivative can be 0 at non-inflection points. If you look at the graph of x to the 4th, that's a good example, or x to the 1/3, you would have your horizontal tangent, but it keeps going. So it's always increasing or always decreasing. It's got to change. It goes from increasing to decreasing or decreasing to increasing to be a true point of inflection. All right, so you just have to be careful. Think of what the graphs would look like. That's why in pre-calc, you should learn what these graphs are going to look like. The parent function, you can add or subtract, move them left, right, up, down, whatever, but generally they're all going to look the same. So you have to know what they look like so you know what's happening at different points. Okay, so let's take a look. We'll come back to that later. Let's take a look at this example. So you have this function. It's a piecewise, and you don't have any directions. But what I want to determine is, where is this function concave up, and B, where is this function concave down? You could think of the functions themselves separately and answer that question, but let's do this algebraically. Let's pretend we don't know what they look like. So first of all, I'm going to look at the interval to the left of 1, so from negative infinity to 1, and my function that defines that interval is 2x. So to find if it's concave up or down, I have to find the second derivative. So the first derivative is 2, and the second derivative, it's not that it doesn't exist, the second derivative is 0. So that implies that there is no concavity. On the interval from negative infinity to 1. Okay, now since we got 0, think of the line 2x. If you were to graph it, it's just so from negative infinity to 1, something like this. Look, the concavity means that there's a change in the slope. But you notice from negative infinity to here, there's the same slope. So there's no change in the slope, so there's no concavity to that graph. Let's look at the second part. So to the right of 1, your function is negative 2, whoops, jumping way ahead here, is negative x squared, and the derivative of that is negative 2x. The second derivative of that is negative 2. So what that means is it's negative, so that means the concavity is down. So it's concave down. On the interval from, it would be from 1 to infinity. And then also we would probably include this point, since this interval does give us from that point inclusive, and so it's going to be inclusive of 1 to infinity, and that's where it's going to be concave down. Let's do one more example here. All right, so on this one, I want you to find all points of inflection. First thing you need to do is think about how to find all points of inflection, and the points of inflection occur where the second derivative is 0. So go ahead and find the second derivative, do this on your own, and then come back and check your answer. So when we find the first derivative, first of all, you could use the product rule, but it'd be easier just to multiply things through. So we'd have y is equal to x to the 3/2 plus 3x to the 1/2 after you take this and multiply it in. And so you'd have the first derivative as 3/2 x to the 1/2 plus 3/2 x to the 2/2, and the second derivative, bringing this 1/2 down gives you 3/4, bringing this negative 1/2 down gives you negative 3/4, and then subtracting 1 from each gives you negative 1/2 and negative 3/2 respectively. Then you want to set it equal to 0, so we set this equal to 0, bring the negative 3/4 x to the negative 3/2 to the right side, reciprocate your x values, so you'd have you'd have what you see here instead of repeating it. And you multiply each side by 4/3, gives you 1 over x to the 1/2 and 1 over x to the 3/2. So we only have two options here. X can be 0, but we know you can't divide by 0. So x cannot actually be 0. X has to be 1. That's the only value that you can plug in here that would make each side true or each side equal each other. So if x is 1, plugging 1 back in up here, you'd have the square root of 1, which is 1. So 1 times 1 plus 3 is 4. 1 times 4 is 4. And so your point of inflection is in fact 1, 4. That's your point of inflection. Okay, so this is it for this video. We learned how to find the points of inflection, to find where the concavity is positive, negative, where it's concave up, where it's concave down, what that looks like graphically, what that looks like algebraically. And in the next video, we're going to use the second derivative test to determine if a point is a maximum or a minimum.